number 1. The process there is they're asking about students and teachers, correct?
Yes.
And they want us to find what?
The ratio of students to teachers.
Okay, so they want us to find the ratio of students to teachers?
Yes.
Okay, so you're saying do a student
It's the
to teacher ratio.
So 2,000.
Okay, and you could write it like so, or you could write it as in like a quotient form, like a fraction. Both are completely acceptable, and I want you to be familiar with both. So I'm going to start off like this. How many students are there?
2,650.
650. And how many teachers?
190.
190 teachers. So you'd think, well, I'm done. I mean, obviously I've written it out as a ratio, and then you would be correct. It is a ratio. However, we always want to simplify our ratio or write it in lowest terms. To make sense of that, let's see. If I look at this table right here in front of me, how many girls and how many boys are at this front table, folks? It's 2 boys, 2 girls? Okay. What's the ratio of boy to girl?
1 to 1.
You could say it's 1 to 1. Does that mean there's only one boy here?
No.
No, one of them would be offended about that, right? Okay. And doesn't mean there's just one boy or just one girl. It means that for every boy there is
1 girl.
one girl. So that's the ratio. That's the comparison of how many people are there. So if we wanted to actually scale up correctly, we would have to say 1 to 1. Well, I have to multiply the 1 by 2 to show how many boys are actually here, right? And the same thing, I would have to multiply
For the girl.
the girls the same number, right? That same scale factor. So that may be a word you haven't introduced in your definition, but guys, when it comes to ratios, scale factor is going to be a big component of it, right? Scaling up by a certain scale factor or shrinking down, which means to multiply. Okay, so I look at this number and I see that I can simplify it. I can see because they both have a 0 on the end. So I could divide both of these by 10. Let me show you a really nice way of writing that. It looks kind of neat. I'm going to put a little arrow downwards. I'm going to put divided by 10. Okay, can we see that okay? Is that too small? Can we see?
Yes.
Okay, let me know, people in the back. If you can't see, I'll definitely try to enlarge. So this will become 265 to 19. I don't know if that simplifies any further, does it? No. So some people are trying to write this as a decimal. That's problematic. So here's why. If we look at the middle table here, let's look at the far table right over here. So that first table on the far right side. What's the boy to girl ratio over at this far table? Boy to girl. 1 to 2. So if we say it the other way around, what's the girl to boy ratio? 2 to 1. Would you simplify that to half, or 1 to a half? Would you say to every one girl there's half a boy? Which half do I have to deal with? Like, what's this supposed to mean? I don't understand. We don't count by half people, do we? So on our ratios here, we generally will want them to be whole number quantities on both parts. Okay, both the mean and the extreme we want to be whole number quantities. So we don't want to rewrite this as a decimal value. So if we can't shrink this any farther down, then that's technically our answer. We're done. If you can shrink it further down, right, simplify it down to a lower term, then you do it. Now, you probably wrote it as a fraction kind of representation, something like this. Am I correct? That's okay if you did. I just want to make sure you know how to do both. So obviously, if we divide this by 10 on top and bottom, you get the same answer, 265 for every 19, which isn't so bad. It's about 14 students, give or take, per teacher. So that's the average, right? All right, second problem. What's the context there? Help me out. Yes, would you please read the problem? Thank you, Miss Aldana. Okay, thank you. So let me just remember when we said there was a ratio of boys to girls 1 to 1 at this table. That doesn't mean there's only one boy here and one girl here, right? That just told us the comparison between them. So that ratio has to stay consistent. So when it tells us our triangle has a ratio of sides that are 2 to 2 to 3, that doesn't say the side lengths are literally 2 inches, 2 inches, and 3 inches. That wouldn't work out because what's the perimeter supposed to be? There's no way you're going to have those numbers and get 392, at least not in my world. So it doesn't work out. There'd be a really crazy base to have to make that work. So what can we say about this triangle, though, based on those ratios? What kind of triangle is it? It's not a isosceles triangle because 2 of the sides are the same, right? So I can draw a picture of that. That would probably be the first thing we should do. And there we go. The first time I drew this triangle, it was incorrect, so this time I finally figured it out. We don't know how long these sides are. All we know is how they compare to each other. So that means the actual length of this side isn't 2, it's going to be 2 times some scale factor, right?
Correct.
Scale up to what the actual number is. So let's just use a variable. If you want to use x, that's fine. Which means this side would also be,
2x.
and then the last one would be,
3x.
excellent. So now we have unknown amounts for each one of these sides. Now we can add them up and set this equal to our perimeter. So now we're ready to go. Okay, so what do we get? 7x? 392? Okay, that's in inches. And then divide both sides by 7. Thank you. That 9's having some issues.
You get 56.
Okay, so x equals 56. So is that my answer? X equals 56?
No.
What is that number?
This scale factor is a scale.
Yeah, that's how much we have to scale up each of the sides by, right? So the question that we are trying to answer is what? What do they ask us to figure out?
What's the longest side?
So which value should I plug this into then?
3.
Obviously, it's going to be the biggest thing, right? It's the biggest coefficient. So 3 times 56, and that's 150 plus 18, which is 168. Thank you. Inches. Nicely done. Okay. All right. That works out very well. All right, last one. So if you noticed, each one of these is matching up with the things you were writing about each term. So ratio, here's a problem about ratio. Here's a problem about extended ratio. So the last box, obviously about
cross product and
okay, so first question for you guys. What is a proportion?
an
An
equation
equation.
stating that the two ratios are equal.
So I know what a ratio is. So you're telling me basically a proportion is just equations made of ratios? Does that sit well? Does that sit well?
Yeah.
So it's just equations that have fractions in them or ratios in them. Okay, cool, excellent. With that being said, the other thing they ask about is cross product. Who here, just by a show of hands, has learned or used the cross product, or also known as the butterfly method, perhaps in previous classes? Excellent. So most of you have already seen this. That's fantastic. You know what? You know how to use it. That's great. My concern is, do you know why it works? Any ideas? Like why we're doing this cross multiplying, like why it actually works?
Make them equal, or to know how to make them equal. Or
Right.
why they're equal.
Yeah, that's my question. How do you know that when you multiply a cross like that you actually do get two things that are equal? I mean, you know it works because you've been using it for so long.
Don't that make us divide?
There's the question. So let's work this problem out, and I want to talk about it. So 3a, the problem says in 3a, what's our proportion they give us?
X over 4, 11 over negative 6. Equal to.
Equal to 11 divided by negative 6. Okay. So the cross product, folks, and maybe this is something you'd want to write as a note to yourself so that way you know why this thing works. I want you to understand the mechanics, right? That's the thing I want you to get from this, because you already know how to use this. The cross product works because really what we're trying to do is we're getting rid of these denominators. Well, how would you get rid of a 4? If you're dividing by 4, what's the opposite of dividing by 4? Yeah, if I multiply both sides by 4 here, the 4 goes away in the denominator. That's the reason we multiplied by it. And then on the other side, you're now going to have 11 times 4. So it moves up here. Similarly with the negative 6, to get rid of it in the denominator, we multiply both sides by negative 6, correct? So if I do that, here's what I end up with. Negative 6 times x. Okay. The 4, of course, canceled out on this side, so that's the only thing left on the left. On the right side, you're going to multiply by 4, so you get 11 times 4. And the negative 6, of course, canceled out because you multiply by negative 6 on both sides to cancel it out with that denominator. Hence, you get this value. So now we have an equation of two polynomials, monomials really. But they're easy to solve, right? Fractions we don't like as much. This is much easier to work with. So what do I have to do to solve this? Yep. Just divide by negative 6. Excellent. So you get x equals 11 times 4 divided by negative 6. Well, I think I can simplify that a little bit. 4 and 6 both are divisible by what? 2. So 4 divided by 2 is 2. 6 divided by 2 is 3. So notice, guys, there's nothing else I can divide out of this. That means when I now carry out this operation, it's already in lowest terms. because you've already done all the simplification. So 11 times 2, 22 over negative 3. That is an improper fraction, but it's in the lowest terms. You can't simplify it anymore.
In other words, 7.3.
Negative 7.
Yeah, but I'm going to write it as negative 7 1/3 because that's an exact answer. Either one, of course, is acceptable to me. I'll accept both.
Oh, never mind.
You okay with that?
Yeah, I was going to say, how did you get the negative, but it's a negative there.
Yep. I actually can do this problem faster. So let's see how many steps we had to take. 1, 2, technically 3, 4. I don't count that one because it's just an equivalent. So 4 steps. Would you agree it's about 4 steps?
Yeah.
I submit to you I can do this in 1 to 2 steps.
No way.
Yeah, in Texas no less. So it's a Texas 2-step. Haha, Mr. Duncan with his bad puns. So I've taught you guys about this, or I intimated about it probably at the beginning of the year. It was something a physics teacher taught me. It's called the slide rule. This is one of my favorite things because it works the same way as the cross product. Mathematically, we're not doing anything different than what we just did. We're just doing it faster, and we're being more efficient about it. So look at this. Look at this proportion. What are we trying to accomplish here? We're trying to get x by itself. So what needs to go away? The 4. So all I'm going to do is multiply both sides by 4, right? Well, that's exactly what the slide rule says. It says if I multiply both sides by 4, this 4 goes from being in the denominator to being in the numerator on the opposite side, right? So basically I've just slid the 4 up here. Now there's still got to be something left over down there. So we have a placeholder. So 1 would be my placeholder. There's still a 1 down there, right? So if I do this problem over again, I say, let's slide this 4 up here and multiply it by 11. That's all we have to do, and we should be able to get our answer. Would you agree? All we're doing is multiplying both sides by 4. It's the same mathematical operation you just did. So I'm going to move him up here. So this becomes x over 1, which is just x, that's what we wanted, is equal to 11 times 4 over negative 6. And now, simplify as before. 4 divides by 2, so does negative 6. And so you end up with negative 22 over 3. So 1 step, 2 step. So you're like, big deal, it's 2 steps versus 4. Oh, well, that cut my workload in high school and a little bit in college down by about half, because everything I had to do was hand computations in high school. Our teachers weren't so keen to the calculator jive, you might say. So we had to do everything by hand. So all of a sudden 6 steps became 3 steps. 8 steps became 4 steps or less, because I was finding these shortcuts that saved me time. So this is just one more thing you can add to your toolkit. You don't have to. All right. Should we do 3B or 3C? We don't need to do both. If you do one, you can do the other. 3C? Okay. Let's see here. Ivana, could you read out 3C for us? I'll write it down.
7 over z minus 1 equals 9 over z plus 4.
Is that Z as in zeta or C as in cat? Zeta? Okay, very good. So 7 over Z minus 1 is equal to 9 over Z plus 4. So here, cross product property is the best and most efficient way to solve this problem. So I'm going to multiply this term, 7, by Z plus 4. So if I do so, I'll write it like this, 7, and then in parentheses, Z plus 4. Try doing X again, habit. On the right side, I'm going to do the same thing. This term, 9, I'm treating Z minus 1 like it's one thing. So I'm going to do 9 times the whole quantity, Z minus 1.
Is it possible you can put it the other way around?
Z minus 1 times 9?
Yeah.
Yes. Multiplication is commutative, so you can change the order of what you multiply. It's still the same. 2 times 3 is the same as 3 times 2. Right? So now we just need to distribute, and then it's a basic algebra question. So 7 times Z, 7Z. I keep wanting to make an X there. It's killing me. 7 times 4 is a positive 28. 9 times Z, 9Z. And then 9 times negative 1 is a negative 9. So make sure you're distributing, guys. I know that's something that a lot of us forget. And now we're just doing some combining of like terms. So 7z goes to the other side, you get 2z. And I'm going to add the 9 to the other side, so I get 37. Is that right? Some funky number. Okay.
How you get 2G?
I subtracted 7z to the other side.
Why you just,
Fair question. And then the last step, of course, divide both sides by 2. So z becomes 37 over 2, which is the same as 18, you say? 18.5 or 18 and a half. Sure. Those are both acceptable answers. 18.5 is the same as 18 and a half, because 0.5 is just 5/10, right? 5/10 is a half. All right, guys, is this sitting well with this? They don't? We better check. Let's check. 7 over 18.5. Okay. 18.5 minus 1. We got to see if that's equal to 9 over 18.5 plus 4. So you get 7 over 17.5. Is that equal, put question marks here, is that equal to 9 over 22.5? Those are some ugly, funky fractions, aren't they? The cool thing is we can scale this up by 2 and this up by 2 and it'll still be equivalent, right? That just gets rid of the decimal part for me. So I'm just going to multiply top and bottom by 2 just to make things a little bit nicer to look at. So that's 35, 14 over 35. And then we're asking the question, is that the same as 18 over 45? So maybe you just made an algebra mistake. That's okay. From here, you can check a number of different ways. You can cross multiply and see if the product is equal. If they are, you're good to go. So I'll say, I'm asking is 14 times, well, let's see, 14 times 45, is that equal to 18 times 35? And I can already tell you it is without doing any actual math, like any actual calculations. You want to see the secret there? So gang, if you can show me that you have the same number of numbers over here, like all the same number of prime numbers over here you do over here, then it must be the same thing, right? If I have 2 times 2 times 5 or whatever over here and 2 times 2 times 5 over here, they gotta be the same thing, right? Well, what's 14 break down to? 7 times 2. And 45 is the same as 3 times 3 times 5, 9 times 5 basically, right? Okay, that's so far so good. On the other side, 35, that breaks down to 7 times 5, or 5 times 7. And 18 breaks down into 3 times 3 times, that's 9 times 2. There we go. So there's 18, there's 35. They're all being multiplied together. So far so good? Is that too crazy for you?
Too crazy.
Well, guys, just look at the numbers. Do we have a 7 on both sides? Yeah, the 7s are both sides, there's a 5 on both sides, there's 2 3s on both sides, and there's 1 2 on both sides. Therefore, these two quantities are the same. So that's, for me, easier than, that's actually faster for me personally than multiplying those numbers out. You're like, I got fast calculator fingers, Mr. Duncan. I will take that calculator any day. Fair enough. Well, would you please turn the page? I don't want to spend an inordinate amount of time on this, but I do want you to see that this slide rule that I speak of is sensible. All right, so there's the picture of the slide rule in all its glory. It just says if you have a proportion, you can move the things, you can move the medians and the extremes around at will. You can move them around wherever you need to move them. So A can move down or D could move up. B could move up or C could move down. This is A over B is equal to C over D. So they can move along that diagonal pathway.
So we can draw that?
Sure. And then I've done so far 2 or 3 examples over the last couple days. And I'm going to ask you to give me a fraction, any fraction you'd like, or ratio, I guess we'd say. Sure, we can use 2/3. I've already used 2/3 once. I've used 3/4 once, so come up with a fraction. It can be any fraction you want. It can be an improper fraction, just a fraction. What you got? No takers.
6 over 36. 21.
10/37ths. Wow, that's funky, isn't it? You guys okay with 10/37ths?
No, we're not doing it.
Those are big numbers. I don't want to deal with those numbers.
6
I'm
over
okay
21.
with. I'm okay with or 6/21. Which would you guys prefer? 6/21 or 10/37? 10/21.
No, it's 6.
We'll meet halfway. 10/21. Numbers from both. Okay, fine. So 10/21. Believe it or not, that's in lowest terms. I don't think you can reduce that anymore. Yeah, because 5 times 2 and then 3 times 7. Okay. I need an equivalent fraction that it's equal to.
That's the thing.
So just scale it up by something.
What we do?
Okay, sure. 30 over 62.
Yeah.
Is that okay? Just scale it up. Oh, 63. Thank you. 63. All right. These are some great numbers. Now, you guys, we basically chose this fraction, right? Just arbitrarily. I want you to then choose what you want me to slide around to prove that the slide rule actually works.
I
Okay.
want you to, can you take this, can you move like from different sides?
Yes, if you want to move just one term, that's fine. If you want to move two terms, if you want to switch two terms, if you want to move everything to one side of the equation,
I'm saying, can we take the 63 and replace it with the 10?
yes, you want to switch them places?
Yes.
Sure. Is that okay, guys, if we just switch them places?
Yes.
Okay, so the 63 is going to go up, the 10 is going to come down. That's what you're saying. All right, so I'm going to write the things that are already in place, just so we already kind of have a sense. Okay, so that hasn't changed. You're telling me move the slide the 63 up. Okay, so there's 63, and slide the 10 down.
Yes, sir.
My question for you is this still equivalent? Are these still equal?
No. 3 is equal to 3.
63 divided by 21 is 3. 30 divided by 10 is? So it is equivalent. It worked. So you agree that this was an equation, that these two things were equal, yes?
Okay, wait, let's do the
All we did was move two things around. I know, it feels like witchcraft, doesn't it? How does that work?
Can we do 21 and 30?
Sure.
You know, that's going to be obvious.
How about we try something crazy? We move everything to one side of the equation.
Sure.
Yes.
Okay, do you want to move everything to the left or everything to the right? What do you want to do?
Right.
Everything to the right? Is that okay? Okay, so I'll take your original equation right here. I'm going to slide everything to the right. Now there still has to be a placeholder there, right?
Yes, sir.
Okay, so 10, I'm going to move it. So the only thing there is going to be a 1, right?
Yes.
And the 21 is just going to be a 1. Now they're both going to slide over. So what was already there, we already had a 30 and we already had a 63.
Do you add them?
No, it's multiplication. It's all multiplication. So the 10 goes down next to the 63, and the 21 comes up next to the 30. Is that right?
Yes.
So there's my question for you. Is 30 times 21 divided by 63 times 10 equal to 1 over 1? You can check it. I can already tell you I know the answer.
It's 630
Okay.
both ways, so that's 1 and 1.
So this becomes 630 over
I
630?
already know 63 times 10 is 630.
If they're equivalent in the first place,
So it's 630.
Right. So what's the purpose of this exercise, right? That's the question.
So it's like
This
what-
is my way of showing you that the slide rule works so that you can use it to solve for variables like we did in that first problem on the other page. Or the last problem, excuse me, on the other page. So this is just helping you to verify for yourself that it actually works. You can say, oh, I can trust it. It does work. Yes,
So
sir.
is it like a way for us to check ourselves? Or I'm not understanding. Like, what are we going to use it for?
This is another way of solving problems faster.
If you have all 4 of them.
Right. This only works for proportions.
So
Yes.
like what? Like how can this get you into a question? Like how can we use it for the question?
Here's me doing the problem, cross product, and then dividing. Got the answer. Here's me using a slide rule. All I did was move the 4 up, and then I solved. It's faster. So this is just another way of solving the same problem. It's just one more trick in your bag, so to speak. Okay? All right, gang. That is it for the slide rule. The other thing was I need to apologize because I had planned yesterday and today, but I figured if I didn't do it yesterday, I shouldn't do it today. It wouldn't be fair to everybody. I was supposed to bring a big bucket full of Skittles and M&Ms that you were going to dip your grimy hands into and take out and then put back, and everybody was going to dip their hands into. So you wouldn't want to eat it anyways. Ugh. There'd be no way. People still do, though, right? There's some all nasty. I don't know what's going on. So this says that if you did that, you would learn something really interesting. And here's what that is. We use ratio to solve a lot of problems. We use it to predict things all the time. So imagine, if you would, that I have this imaginary bucket that I've mixed in. And let's make them peanut butter M&Ms so they're bigger, so they look different than the Skittles. Because that's just rude to try and eat Skittles and M&Ms at the same time, right? Like, ooh, M&M Skittle. Oh, that's hard. Ooh, chew carefully. So we're going to mix them in. So I mixed them up really well, and let's assume that I've mixed it up really well so it's pretty uniform. Everything's pretty evenly distributed throughout. If you were to reach in and grab a big handful, because we're greedy like that, and we looked at what was in our hand, and let's say the ratio that we saw in our hand came out to be something like 13 Skittles and 7 M&Ms. Yeah, not very big. Not everybody has massive man hands, so that's fine. The question is, well, what can you do with that information? Well, guys, believe it or not, we can scale those numbers up accordingly to any size we need to. So we can actually figure out, if we know some more information, we can figure out everything about that, what's in that jar. If you tell me how many things are in there total, I can figure out how much stuff is in that jar. If you tell me how many of these are M&Ms, I can tell you how many of the rest are Skittles. Just from that one handful you pulled out, you can estimate with pretty decent accuracy, as long as your handful's big enough, what the actual amount in the jar is. We use this principle, it's called extrapolating, all the time. I used to live in an area where they would announce the air quality every day, so you would know whether or not to go outside because the air was not good enough to breathe. It was because the area had this strange inversion. It basically makes all the particulate that comes into the atmosphere, it couldn't escape and go out into the wider world and dissipate and whatnot because it was being held in, okay, kind of like a bubble. So some days that happened. Now, if they announced there's too much of this particulate or pollution or smog in the air, you shouldn't go outside today because the air's quality is really poor. It's not good for you. It's not good for your health. How did they know that for the entire region? Did they measure every single cubic foot of air? Right. They didn't measure every single cubic foot of air in the region. Instead, what they did is they took a couple samples, right? Maybe several samples. And said, okay, these samples are pretty representative for what we're seeing, like for the entire region. They're pretty good representation. They measured the air quality in those few samples, kind of got an average between them, go, okay, this is what we're seeing across these samples. And they then said, this is what the entire area looks like. The entire region looks just like this. So is that exact? No, it's going to be off a little bit, but it's going to be pretty close enough to be accurate. This is how we do voting, believe it or not. How is it the media always seems to know who the candidate that's going to be president is before the votes have been counted? Did they ask every single person who's ever voted? They don't have time or resources to do that. So what do? Well, they ask a sampling of people. And then they use that sampling to extrapolate out to how the entire population was voting. So it's a ratio which they've extrapolated out. They've expanded it out to match the entire population. But it has to be a good size. So that's the big thing here. So let's just test this out. Now suppose I told you that there were 253 M&Ms. My question is, about how many Skittles must there be? So here's how I would set it up. My ratio right now is 13 Skittles to 7 M&Ms, correct? I want to know if I had 253 M&Ms, how many Skittles do I have? Maybe I should use the letter S for Skittles. Maybe I should use more color. Should I use more color?
Yeah.
Taste the rainbow. All right, so there's my proportion, right? I just want to scale this up until it looks the same size, right? So now you can use cross product if you want, but I think just scaling up by using the slide rule is a lot easier. So all I'm going to do is 253 times 13 and divide that by 7. So tell me what you get. Solve for us, please. What do you get?
I got a large number, but I'm not sure if it's right.
It should be. Yeah. Yeah, that sounds about right. That sounds about right. How do I know that? Because look, 7 compared to 13, that's almost twice as big, isn't it? But there should be almost twice as many Skittles. Well, if there's 253, almost twice as big as 253 is like almost 500. It's like 490 something. So that's just me kind of eyeballing it in my head. So what number did you come up with?
469.8.
469.8. That's a problem. Do we having parts of Skittles? Which way should we round?
469.
So it's either somewhere between 469 and 470, because we're counting whole Skittles, right? This is an estimate. So since it's an estimate, we're not going to get an exact number amount unless we're told, hey, what's it going to be round down if you have to? They'll let you know round down or round up, right? In this case, we could do either because we haven't been given a context. So we know that there should be approximately 469 to 470 Skittles in this jar. So we can put either one. So I would say approximately, so this means approximately 469 to 470 Skittles. Which way do we round? Well, it really depends on the context of the question, right? If we were just told, hey, just round it up, okay, then we could round it up. If I said, hey, I want you to tell me how many would be at most whole number Skittles, well, if this was exact, then it couldn't be 469.8. It would have to be 469. That'd be the nearest whole number amount that's not been rounded up, right? But this is going to happen to you, right? You're going to get numbers that look weird. You're like, they can't be part of a Skittle. Well, I guess it could be, but it should be a part of a Skittle based on what I have. But your handful is only a small sample size, isn't it? So you need to go back in, take another handful, and see if you got the same ratio again. If you did, okay, you should feel consistent with it, right? So that's called extrapolating. All right, turn the page. I'm going to save you from having to listen to me drone on. I'll just let you copy this down. It'll save you some time. And then we'll explain and talk about it in a minute.